Okay. All right, so I'm looking at the very bottom of page 4. I'll review a little bit and then catch us back up. So talking about enzymes, enzyme connect. Do you guys have any questions before I get going, or just?
I wasn't lost, but it seemed like everything was happening so fast with the graph and the transitional state and the delta G, and I was just
Okay.
like, what's going on? So I watched the video again, and I was like, I don't know if we're gonna start start from there or.
So let's see. Well, let me start bottom of page 4, and if I need to come back and review something, maybe we'll take it from there. All right, so we've got an enzyme plus a substrate can come together and form an enzyme substrate complex, and the substrate can then turn into product. And actually with all the arrows, just getting started. And by the way, I think both of you had given me your homework assignments a while ago. So there is the one due today.
I uploaded it to the comment on it.
Okay, yeah, okay. So I'm just kind of going back and reviewing, picking up a little bit of a review.
Oh, thank you.
You're welcome. There you go. So at the bottom of page 4, I'm going to pick up on page 5. So an enzyme can bind to a substrate molecule and become an enzyme substrate complex. It could let go of it and never turn the substrate into product. So that we could just, because of the reverse arrow, we could just go back and the enzyme could bind the substrate, let it go, nothing happens. Or the substrate could turn into product and we can end up with product. By the way, if most all reactions are reversible, an enzyme could pick up a molecule of product and turn it back into substrate. So that could happen as well. All right, so to follow the kinetics, to measure what's going on, to kind of look into like how fast is the enzyme working. So since that's the job of an enzyme is to make a reaction go faster. So how can we analyze that? So the analysis of the rates of the reaction, that is enzyme kinetics. And again, the basics here were figured out by this team, Michaelis and Menton. So what we're going to do is we're going to mix enzyme and substrate in a test tube or in a beaker or whatever. And we could think about how the concentrations of these things change over time. So we can start off with a certain amount of enzyme, and we can start out with a certain amount of substrate. So typically we have considerably more substrate than enzyme. And when we mix them together, something's going to start to happen. So the enzyme will start to combine with substrate. So we're going to see the amount of free enzyme drop, and we're going to see the amount of substrate start to go down. And we're going to see the formation of enzyme substrate complex. So hard for me to write all this stuff in here. And then at some point, we're going to see the formation of product. We'll start to form product. So as the enzyme gets turned into enzyme substrate complex, product substrate starts to get turned into product. And if we have a lot more substrate than enzyme, we should end up kind of saturating the enzyme. We should end up turning most of the enzyme molecules into enzyme substrate complex. So if I have, I'm not going to draw this, but if I had 10 enzyme molecules and I had 10,000 substrate molecules, pretty quickly substrate should attach to all of the enzyme. And until the amount of substrate goes way down, I should have my enzyme saturated. I should have almost all of the enzyme in the form of enzyme substrate complex. And for a period of time, I should have a consistent rise in the amount of product. Eventually, as the amount of substrate comes down, eventually it will taper off. Eventually the reaction will come to an equilibrium. So what we want to do is we want to measure the velocity of the reaction in that initial phase of the reaction. So that is called the initial velocity, and we're measuring the change in the amount of product over the change in time. And a couple things are going to start to happen to kind of simplify our analysis. So I'm not super calculus math guy by any means or anything, but just analyzing this reaction with the 3 different steps and the arrows back and forth makes for a fairly complex analysis. We're going to start to find ways to simplify it. One way to simplify it is by measuring the reaction early in the reaction. We can ignore this backward reaction. We can ignore that because if we measure the velocity early in the reaction when the amount of product is very small, we can ignore the amount of that reaction going backwards. Are you with me there? Mm-hmm. If I have almost 0 product, then the backward reaction here, I can get away with ignoring that. So we're going to use this reaction here, and we're going to, thanks to Michaelis and Menton, we're going to make some additional assumptions here. So one of the things that Michaelis and Menton figured out was that in most reactions, in most enzymatic reactions, we have what is called the rapid equilibrium assumption. And that is basically going to say, I'm going to put some numbers to these rates. So this forward reaction can be, we're going to call that reaction rate K1. We're going to call the reverse reaction rate K minus 1. So these are little k's for rate constants. So you have K1 for the forward, K minus 1 for the reverse. This would be K2, and then we would have a K minus 2, except we're saying since we're doing the initial velocity and ignoring the product, we're going to ignore K minus 2. Okay. So based on their experiments, I don't know if they hold true across the board, but based on Michaelis and Menton's experiments, they come up with this thing, so the rapid equilibrium assumption. That basically says that K1 and K minus 1 are much faster than K2. What that means is simply that the enzymes and substrates are bouncing into each other and combining and letting go of each other much faster than the number of times that substrate actually gets turned into product. So when you mix enzyme and substrate together, they start rapidly, don't hurt yourself, they start rapidly combining and letting go, and occasionally we will turn one of the substrates into product. So K1 and K minus 1 are considerably greater than K2. Just kind of getting started on page 6. And everybody gets a book. Okay, so if you have time to start reading it, if you're busy with other stuff, that's fine. Yeah, but if you have the chance to start reading it, maybe at some point here and there we can talk about it, or if you got questions or something. Okay, so and K2 therefore becomes, K2 is the rate limiting step. I don't know if you guys have ever heard that expression before. I think maybe so. So K2 is rate limiting, and we're going to rename it. We're going to call it Kcat, as in catalytic. So Kcat is what's going to determine really the rate at which the reaction goes. So Michaelis and Menten, we're dealing with a very simple reaction here. Simple reaction, one substrate gets turned into one product. It's a one-step thing. We got rate constants. We got a forward rate constant K1. We've got a reverse rate constant K minus 1. We got a rate constant K2. And initially, or we might think we have a reverse rate constant K minus 2 because we are going to measure the initial velocity before we form much product. We're going to ignore K minus 2. And because K2 is going to be the rate limiting step, we're just going to give it a different name. We're going to call it Kcat to indicate that that's the rate limiting step. All right, so we're going to wave a wand or whatever and skip through all the mathematical analysis because I'm not smart enough to figure it out or whatever, but we're going to, based on these assumptions, based on this idea, Michaelis and Menten, we're able to, hey, I'm just kind of at the beginning of what I'm doing right now, but so Michaelis and Menten come up with an equation that relates the velocity to the substrate concentration. So we're going to get this equation that is known as the Michaelis-Menten equation. The initial velocity is going to equal, make sure I get it right, Vmax times the substrate concentration over Km plus the substrate concentration. So I'm going to want you to learn this equation. So this is known as the Michaelis-Menten equation. So for a given enzyme, the velocity, we can relate the velocity to the substrate concentration. There's your copy of The Immortal Life of Henrietta Lacks.
Thank you.
You're welcome. There you go. Okay, so, and what this is going to do, what this would do in practical terms, this would allow us to have an enzyme and measure how fast it works. And I'll talk in a minute about, we could add different things to it to see if that inhibits the reaction or makes it go faster or makes it go slower, whatever. So we've got this basic enzyme here, and it's going to tell us about properties of the enzyme. So Vmax is how fast that enzyme can work if we saturate it with substrate. Km is basically going to be the dissociation constant for the enzyme and substrate. So to refresh just a little bit and catch, okay, so we want to be able to analyze how fast an enzyme can turn substrate into product. I've got the little diagram here again. If we mix together some enzyme and substrate, what's going to happen is enzyme is going to start combining with substrate. So the amount of free enzyme, it's hard to see, let me maybe start this over again. So we start out with enzyme and substrate. When we mix them together, we're going to see a decrease in the amount of free enzyme. What's happening to our enzyme? It's combining with substrate. Okay, so we're going to see the amount of free enzyme go down, and we're going to see a rise in the amount of enzyme substrate complex. And as substrate starts to get turned into product, we're going to see a decrease in the amount of substrate, and we're going to see an increase in the amount of product.
All right, can you say that over again, please?
Okay.
From the, yeah, go.
So we're going to put enzyme and substrate together.
Right.
Typically, we add a lot more substrate than enzyme. So if I had, I don't know, I'm making up numbers just to make a point. If I had 10 enzyme molecules, we would have 10,000 substrate molecules or something. So we got a lot more substrate than enzyme. Mix them together. What's going to happen is enzyme is going to start to combine with substrate. So the amount of E, the amount of free enzyme, starts to go down. And we see enzyme substrate complex start to appear. Right? So the amount of free enzyme goes down, the amount of enzyme substrate complex starts to go up. By the way, the amount of enzyme substrate complex can never go higher than the amount of enzyme. So it's going to quickly flatten out.
Okay.
So you go back to like where you started from?
So yeah, so if I had 10 enzyme molecules and I have 10,000 substrate molecules, what's quickly going to happen to those 10 enzyme molecules?
You know we have.
They're going to bind substrate, so the amount of free enzyme is going to go down to close to 0, and the amount of enzyme substrate could never get higher than 10, but it'll approach 10. And as long as I've got a lot of extra substrate for some period of time, we're just going to keep the enzyme saturated with substrate. Are you with me on that?
Yeah.
Okay. And that enzyme, every time the enzyme turns a molecule into product, there's another substrate molecule ready to go. Right? So imagine, in a factory or something, you give your workers parts to build something, and as long as you keep giving them parts, they keep building whatever they're supposed to build. So as long as we keep giving the enzyme substrate, it'll keep making product. The amount of substrate will decrease, the amount of product will increase until you come to whatever the equilibrium is. Eventually you would come to some we're not necessarily going to turn all of the substrate into product, because the equilibrium might be that you come out with half and half or something, so whatever. Hey, just kind of review, you'll have to kind of catch up at some point. I am recording, but going over, I'm kind of on page 5 of the notes if you follow along. All right, so these scientists, Michaelis and Menton, are looking at this. They're studying enzymes, they're looking at data, they're getting results or whatever. A couple things they figure out. One of the things they figure out, they end up calling the rapid equilibrium assumption, is that when you mix an enzyme and substrate together, very quickly enzyme and substrate molecules start binding and letting go.
Okay, when you mix.
So very quickly, enzyme and substrate molecules start hooking up. And they don't always turn the substrate into product. So look at the arrows. An enzyme molecule could grab a substrate, but just let go of it without the reaction happening. So if my chemical reaction is to take my black marker and turn it into the black marker is substrate, the blue marker is product, I can grab the black marker and magically turn it into Well, a lot of the time, the enzyme just grabs the substrate and then just lets it go without anything happening. And that's happening very quickly.
So why, and you said it like, for the second part, it doesn't always make a product?
Correct. That's kind of saying the same thing. So an enzyme can bind a substrate molecule and let go of it without turning the substrate into product. So K minus 1 is the reaction just going, so the enzyme and substrate can come together. Amy, what are the two, after an enzyme binds the substrate, what are the two things that could happen? Well, hang on, I'm putting her on the spot.
What are the two things that can happen?
So from here, what are the two things that could happen?
You could either change the structure or.
It could change the substrate into product, or it could just let it go and be back. So if
It's
it,
kind of like the, what we talked about last time, about oxygen or.
it's correct. It's like, right. So a hemoglobin molecule can bind to an oxygen molecule and then let it go. The difference is the hemoglobin never turns the oxygen into something else. The hemoglobin only has the option of binding and letting go. Here with the enzyme, we have the option of the substrate molecule turning into a product molecule. And because because K minus 1 is much faster than K cat, it's actually more likely that the enzyme will just let the substrate go than it will turn it into product. So that falls under this thing here. So that just affects the mathematical analysis, which I'm not going to go that far into. So K1 and K minus 1 are much faster than K cat. All right, so two big assumptions for Michaelis and Metten to put this equation together. One of them is that we're going to measure the initial velocity. We're going to measure the formation of product very early in the reaction so that we can ignore the back K minus 2. So we can ignore this. And then the other thing is that K1 and K minus 1 are much greater than K cat, also known as K2. With that given, we get this equation, the Michaelis-Menten equation. This is your big equation for Unit 2. We got Henderson-Hasselbalch for Unit 1. We've got Michaelis-Menten for Unit 2. So the velocity of the reaction is going to equal Vmax times the substrate concentration over Km plus the substrate concentration. And we can do an experiment. I've done these when I was in graduate school. We could do an experiment where we measure the velocity at different substrate concentrations. So I give my enzyme 1 millimolar substrate, I give it 5 millimolar substrate, I give it 10 millimolar substrate, give it different amounts of substrate, and I can measure the initial velocity at that substrate concentration. And we're going to end up with a curve that looks like that.
That's 5.
That's supposed to be a 5, sorry, yes. I'm just making up numbers. Okay, so we're going to get something that looks like this. This is a Michaelis-Menten plot. The words are in the notes, but just FYI, M-A-E-L-I-S and Menten. Okay, we're going to get a plot that looks something like that, and it's going to level out at, forgot to say what's on. So this is velocity. This is the velocity. It's going to level out at Vmax. So what is the highest velocity we can get? The highest velocity we can get is going to be Vmax. And our Km, this is going to get back to that stuff we were doing with the ligand binding. Km is going to be our dissociation constant. Now, with our ligand binding from before, we had M plus L, we only had a forward and a reverse. We only had a forward and a reverse, that was it. We don't turn the ligand into something else. And the dissociation constant was the reverse over the forward. Okay, so the reverse reaction is when they dissociate. The forward reaction is them coming together, so the dissociation constant is the ratio of the reverse to the forward. Okay, now, with the enzyme, there are two things that the enzyme substrate complex can do. It can dissociate, it can just go back, or it can turn into product. So Km is going to equal K minus 1 plus K cat over K1. So we bring an additional term into it. However, what did I say about K1 and K minus 1 compared to K? By the way, if you missed it before, I'm interchanging the words K cat and K2. They're the same thing. So this reaction here is K2, also known as K cat because it's the rate limiting reaction. So again, Michaelis and Menton figure out these two things happen really fast. These two rates are really fast. So enzyme and substrate are just letting go, coming together, letting go, coming together, letting go, coming together really fast. Occasionally, the substrate gets turned into product. So we could call that K2, but they decided that because this is the rate limiting step, this is the step that determines how fast the reaction is going to go, we're going to give it a different name. We're going to call it the catalytic step, or Kcat. So if I say, I'm going to mix up the terms Kcat and K2. But because these two are much faster, if K minus 1 is much greater than Kcat, mathematically, what can we do here to simplify this? We can just ignore the Kcat. So like if K minus 1 was 1,000 and Kcat was 20, we can basically ignore Kcat. So our Km basically becomes the dissociation constant for enzyme and substrate.
And the reason we took off Kcat is because it barely happens.
It is because, like, numerically it's going to be much smaller than this, so it doesn't really matter.
Okay.
If I had, so just for the sake of an exercise or something, just do this real quick. So let's suppose that K1 equals 700, K minus 1 equals 1,000, and K2 or Kcat equals 15. So imagine those are the numbers. Calculate these two things. So this is real quick. Just do this on your calculators real quick. Do that Km, do that Km. So for the one, you're going to use all three of the numbers. For the other, you're just going to use the two. And you should find out that you come out with pretty similar answers. So everybody gets a copy of that book. You don't have to do anything with it, so that is a gift for you. I don't know how busy you all are going to be over the next few weeks, but if you have a chance to start looking at it, we could once in a while ask questions or talk about it, but up to you. So if I do all the numbers, if I do the whole thing here and I get 1,000 minus 15 is 985 divided by 700 equals, I get 1.41. And if I ignore the k-cat and just divide 1,000 by 700, I get 1.43. So just to illustrate the point that as long as k minus 1 is considerably larger than k2, we can just ignore it. Are these two things equal? No, but they're close enough. All right, so to the yeah.
Is this exam 3 or 2? Is this gonna come out in exam 2 or?
Yes, this is, yep, and which by the way is a week from Thursday.
Okay.
Yep, so I'm pretty close to wrapping things up. I may not wrap it up today, but I'll pretty close. I will wrap things up Thursday. And then Tuesday of next week, we can do some combination of, if you have questions, I can review. If you don't have many questions, I can start moving forward, but whatever. By the way, if you haven't gotten to me one way or another, there is a assignment due today. There was an assignment due today. I know some of you have already sent it to me. If you need to give it to me, give it to me. And then the next homework assignment is due Tuesday of next week, I believe. Does that sound correct? There's an assignment based on what I'm doing today, and that'll be due next week. Let's do it on Tuesday. Okay, so based on these data, the practical impacts here, I can determine how fast the enzyme is, and I can determine how well it binds to the substrate. So Km is going to be a measure of how well the enzyme binds to the substrate. And remember maybe you remember, hopefully the homework assignment today was supposed to kind of help make that point. If a molecule has a smaller dissociation constant, that means it binds it better, binds it tighter. So the smaller the dissociation constant, the more it binds. That's what we're going to see with the Km. So a smaller Km, that means the enzyme binds that substrate better. Okay, so I can look at a plot. So I could take an enzyme, I can measure the velocity at different substrate concentrations. And I can make a plot like this. From that plot, I can estimate that enzyme's Vmax, and I can estimate Km. So before, we had a similar thing where when the molecule was half saturated, at half saturation, you would get the Kd. Well, what happens here, what happens to this equation if Km equals S? So if Km equals S, I get S plus S, that's 2S. What happens to my substrate concentrations? They cancel out. So when the substrate concentration is equal to the Km, the velocity is 1/2 of the Vmax. So that means if this is my Vmax, I can go to half of the Vmax, and that is my Km. Okay, so to just blow your mind. Okay. So let's go back a moment to the ligand binding, where did I have this? Okay. So, I'm going to erase this here for the moment. This here, the first part of this equation, is basically just like our ligand binding. So we've got a molecule, in this case it's an enzyme. We've got a big molecule, this is the enzyme. We've got a small molecule that is the ligand, and they can come together. They can come together, they can let go. They can come together, they can let go. We can define a dissociation, it's kind of like an equilibrium constant, but we're going to call it the dissociation constant because we're going to look at it going backwards. How much does this want to go backwards compared to forward? By the way, this was at the top of page 2. So it's going to be, or if this is the K, what terms did I use? The K on and K off. So this is the ligand coming on. This is the ligand letting go. We go back. This would also be equal to K off over K on. If these two things don't want to be together, that means I'm going to have more of this than this. That would be a larger dissociation constant. If the two like to be together, if the two want to come together, then I'm going to have more of the ml, and I would have a smaller dissociation constant. Now, something happens with this equation when 50% of the, when half of the macromolecule has the ligand attached to it. So suppose I've got 4 of these macromolecules, and I've got some ligand, and 2 of the macromolecules have the ligand bound. So the amount, at that point, the amount of free macromolecule is equal to the amount of molecule that has ligand bound. Right? Well, by my numbers here, how many mLs do I have? 2. How many M's do I have? 2. So M equals ml. What does that do to the equation? That means Kd equals the ligand concentration, right? Because if this equals that, they're going to cancel out. So we have this rule that at 50% saturation, that amount of ligand is equal to the Kd. So if I had a hemoglobin, an oxygen, or something else, some other thing, here's the different ligand concentrations. If I find the 50% saturation point and go down, that number equals my Kd. That's just the way it works. If you ever, most of you will probably never have to apply any of this, right? But if you were to go to work for a pharmaceutical company or something or whatever, and you're doing experiments, that could be something you had to do at some point. Okay, but because of the relationship of this equation, when this equals that drops out. That's the ligand concentration that would be equal to the Kd. Something similar is going to happen because something similar is going on. With this, we're not turning it into a product, but we still have these two things coming together. And we have enzyme coming together with substrate. And because we can ignore that step, basically my Km is basically just looking at that the way we were looking at this. And our mathematical relationship shows us that, again, something happens at the halfway point. At the halfway point, our substrate concentration equals our Km. So at half Vmax, what fraction of your enzyme is turning out product? At half Vmax, what fraction of enzyme is turning out product? Half of it. So half of my enzyme has substrate attached. So it's the same, I get it, I get there, but it comes down to the same basic concept. So I could take an enzyme, measure velocity at different substrate concentrations, and from those data I can determine a Vmax and a Km. I learned two things about my enzyme. I learned how fast it can crank out product, and I learned how well it binds to its substrate.
So when we count the initial velocity, like when we do that one, that only happens at 50%?
Now, the initial velocity happens at different concentrations. I can measure the initial velocity at different substrate concentrations. The substrate concentration that gives me half of the Vmax gives me the Km. So I might get velocity. I can do an experiment where I do some different substrate concentrations. So substrate concentrations, I'm going to use 1 millimolar, 2 millimolar, 5 millimolar, 10 millimolar, 15 millimolar, and 20 millimolar. You don't need to write this down. Okay. At each of those substrate concentrations, I'm going to get a velocity. Okay, and an analogy that comes to mind to sort of figure this out, I don't know if this is going to help you or not, or it's just me being weird or something or whatever, but you've all been to a grocery store or whatever. Now, these days when you go to a grocery store, they got all the self-checkouts. We're going to go back in time to a day before the self-checkouts. Okay, so we've got four cash registers, and at each cash register there's somebody checking out people. Okay? So suppose I put 50 people into the grocery store. Okay, so I put 50 people into the grocery store. They're going to go shopping. Eventually they're going to start checking out. I could count the number of people that get checked out. Okay, so with 50 customers, I'm going to use a small number. With 20 customers in the store, let's say that we get 2 customers checked out every 5 minutes. Okay, so if I put 20 people in the store, say go shopping, they're going to start hitting the cash registers. We can check out 2 people every 5 minutes. Okay. What's probably going to happen in that number if I do the experiment again and I start off with 40 customers in the store?
It's gonna take longer.
It's not how long it takes to it's how fast are we checking them out. What's going to happen in the number of people going through the checkout lines? I'm going to get more. If go into the grocery store, and there's only 20 people in the store, how frequently how many people are going to be at the checkout lines? Not that many. What happens if I put more people in the store? There's going to be more people there's going to be more people checking out. And as long as the people at the cash registers can we're going to check out more people. Are you getting that now? Okay, so I'm not asking how long it's going to take to get all of them checked out. I'm saying how many people are getting checked out every 5 minutes. And as I increase, if I only put 1 person in the store, how many people can get checked out? Only 1. So that's not I'm not going to get many people checked out. If I put 20 people in the store, let's say that I get 2 people checked out every 5 minutes. If I put 40 people in the store, there's going to be more people hitting the checkout lines. So it goes up to maybe it doubles. Maybe it goes to 4 people every 5 minutes. I put 60 people in the store. I might get more. Now I get 5 people checked out every 5. Now eventually what's going to happen, eventually I'm going to reach a number where all of my checkout lines have people in them. And if I add more customers, we can't get them checked out any faster because the 4 checkout lines are full. That's the point where it becomes saturated. Are you with me?
Yes.
Are you with me? Okay. So as I keep adding customers into the store, I can check out more people. I can get until I get to the point where there's so many customers in the store that the lines are all full, and we can only go as fast as the checkout people can check them out. That's my Vmax. That's where we're saturated. That's where we're at Vmax. Okay, so I can do that. So I put some enzyme in a test tube. I give it some substrate. I measure my velocity. And maybe my velocity here is 10 micromoles per minute or whatever. I don't care what the units are. I double the amount of substrate. I get twice as much product. I do a little more than double it again. Let's say it goes up again. Now at some point I'm going to start getting close to saturating. So now maybe say it goes up to 90 and then 100, and then it kind of flattens out at 100. So at this point, at this concentration, I've just about filled up my enzyme. I've got all the enzyme molecules working. Giving them more substrate doesn't get them working any faster. So that's my Vmax. If I plot those data, so what am I going up to? I'm going up to 20 millimolar. So there's 10 millimolar. There's 20 millimolar, there's 5 millimolar. So my data points at 1 millimolar, I've got, and I'm going up to 100. I just picked the number 100 for no particular reason, so don't put any thought into that. So at 1 millimolar, I'm at 10. At 2 millimolar, I'm at 20. At 5 millimolar, I'm at, I should have gone up higher than that, but at 5 millimolar, I'm at 50. And then at 10 millimolar, I'm at 90, and then 100, and then 100. Okay, so I would get data that looks something like that. From those data, I can estimate my Vmax. I'm going to estimate my Vmax is about 100. And I could estimate a Km. How do we estimate a Km? Well, our equation tells us that the Km is going to be equal to the substrate concentration that gives us half of the Vmax. So at the half of the Vmax, that should come out at about 5 millimolar would be my Km. Red or blue, which one has a lower Km than the one I started with? So the blue has a lower Km, so the blue would have a lower Km. What does that tell me about it?
The lower the KM.
It doesn't have the fast.
Isn't binding fast?
A lower Km means it binds better.
Better.
A lower Km means it binds the substrate better. And at a lower concentration, I get a faster velocity. So for the blue, compared to my initial black, the blue, at every concentration, the blue works faster. That's because it can bind the substrate better. The red one, the curve for the red, has a higher Km means that it does not bind the substrate as well, and therefore it is slower at every substrate concentration. Just for the heck of it, I drew curves that all have a similar Vmax. They don't all have to have the same Vmax. They could have different Vmaxes. But so I discover an enzyme. What might I want to know about it? How fast can that enzyme make product? So I can measure the Vmax. What else might I want to know about it? I might want to know how well does that enzyme bind substrate. So we can get from our velocity and substrate, we can determine a Vmax and determine a Km. And this is bringing us close to the end. Okay, so at the bottom of page 6, there's something for everybody to fill out here real quick. I'll write it up here. You can write it in. So our Michaelis-Menten equation, initial velocity equals Vmax times substrate concentration over Km plus substrate concentration. Another just little thing about the analysis here, we're going to look at what's going on at the different substrate concentrations. So this equation is a FYI random bit of information. This equation gives us a hyperbola. So the curve that goes up like that and flattens out, that's called a hyperbola. I think one that goes like that is a parabola or something like that. So now at low substrate, I'll do it the way it's in the notes. At very high substrate concentrations, when the substrate concentration is much higher than the Km, so if the substrate concentration is much higher than the Km, think back to what I was saying before about when we're adding two numbers together, if one number is much bigger than the other, what can we do? We can ignore the small one. So if substrate concentration is much greater than Km, we can ignore Km. And what happens at high substrate concentrations, the velocity is Vmax. Okay, so if the substrate concentration is much higher than the Km, our velocity is just going to be maxed out at Vmax. When substrate concentration is much greater than Km, the initial velocity simply equals Vmax. Okay, so I drew a curve here in black. I made up some numbers. Okay, so let's say we've got these concentrations. These are my velocities. Just made up some numbers, kind of made a graph. Where it peaks out, that's my Vmax. So my Vmax would be 100. Half Vmax gives me the Km. So the Km in this case would be about 5. I drew two additional lines. I drew a blue line and a red line. Blue or red, which one binds substrate better than the, you guys already know this or shouldn't. So I'll phrase the question a different way. Blue or red, we'll let Amy answer it. We'll put the pressure on her again. But blue or red, which line represents an enzyme that binds the substrate better? You got a 50-50 shot.
We talked about this last class year.
Correct.
I think it's
What does K, so a lower Km or a higher Km, which one binds better? Binds better when it's lower. So the blue, you said it correct. So the blue would have a lower Km, saying it binds enzyme better. Notice that at any given concentration, the blue is faster. The blue has a higher velocity no matter what the concentration is. The red, on the other hand, would have a higher Km, and at any substrate concentration, the red is the slowest. And so if it binds better, it's going to be faster. All right, our Michaelis-Menten equation, we're just going to look at that curve again. When the substrate is much higher than the Km, we can ignore Km. Substrate cancels out substrate. So if the Km is low, if the Km is small, or if the substrate concentration is much greater than Km, we can ignore Km. That cancels, the velocity is Vmax. So at high substrate concentrations, our velocity is Vmax, approximately Vmax. When the substrate concentration equals Km, when the substrate concentration equals Km, then the velocity equals 1/2 of Vmax. Oops, not S, but 2. So when the substrate concentration equals the Km, when these two things are equal, I'll do the math one more time, when these two things are equal, that's like having S plus S. S plus S is just 2S, and then my S's cancel Vmax over 2. So when the velocity is half of the Vmax, the substrate concentration is equal to the Km. Or when the substrate concentration equals the Km, that's going to give me a velocity equal to half the Vmax. And then lastly, if the substrate concentration is much smaller than Km, Km plus S, S. So if the substrate concentration is much smaller than Km, then I drop that. We now have a linear equation. So remember, linear equation, y equals mx plus b, but in this case our y-intercept is just 0. And notice at low substrate concentrations, it basically just, the velocity just goes up as a linear function of the, so at low substrate concentrations, we've got a line. At very high concentrations, it's just constant, flat out at Vmax. In between, we have the curve. All right, I'm going to throw one more thing at you for today. So, in reality, when you do an experiment like this, the data typically make it hard to determine an accurate Vmax. So if I actually did the experiment, velocity, substrate concentration, if I actually did the experiment, I might get some data points that look like that. Okay, and it's going to be difficult to determine what my Vmax is. So let's say I had 10, 20, 30, 40, 50, 60, 70. Am I going there? Am I going, where am I maxing out? It's hard to determine. We can have a computer do it. So we could put data into a computer, have the computer fit a curve to that and tell you what the Km and the Vmax are. However, a little bit of error in one of those data points. And have any of you done like a research project where you actually were doing some kind of experiment and collecting data? So you may be aware that the data don't always come out all that clean. Okay, so the data often don't come out that great. And so when you're fitting data to a hyperbola like this, if one of those data points is off, it can have a big effect on what you get for your data. So this is not a good way to get consistent results. So somebody figured out we're going to rearrange the equation so that it fits a line, so that the data come out linear instead of a curve. So this is called a Lineweaver-Burke plot. This is on page 7. Oops, no E at the end of Burke. So what they figured out, or somebody figured out, I guess they figured out, is we can just take our Michaelis-Menten equation and do what is called a double reciprocal plot. We're going to take our equation, turn it upside down. So we're going to go 1 over V sub 0 equals Km plus S over V max times S. I can break this out into, I'm not going to make you do the math here, but just if anybody was curious, maybe you're not, but I can do Km over V max plus S over V max S. So again, I'm not going to make you do this, I'm not going to have you do it, but just to follow through. So this is just that upside down. So this is just the reciprocal of that. Then I'm going to take my Km over that plus my S over that and just spread it out. So if I had A plus B over C, that would be the same as if I took A over C plus B over C. If you're with me there. What happens to my substrates? They cancel out, so I end up with 1 over V max. And I'm just going to write this as, I'm just going to put a 1 over there so that you can just see there's a 1 over the S. So now I have a linear equation. Y equals mx plus b. So my slope is Km over V max, that's the slope. My y-intercept is 1 over V max.
How did you get the 1?
So,
Missed the bird.
right, so when I have Km over V max times S, how do I explain this? Suppose I had Q over RT. I just want to show, I want to separate out the T. I want to make the T look, I want to show like QR times T. But I want to kind of separate that T out, so I'm just going to put a 1 over it. So, maybe a math teacher would have a better way of explaining that, but so Q over RT, would we agree that that is the same as Q over R times 1 over T? So what I want to do is I want to get that substrate concentration out of there. Because what am I plotting here? I'm plotting the velocity as a function of substrate concentration, so I need to get that substrate concentration separate from the Km and the V max. So I'm just pulling the T out of it. I don't know if there's a better way to explain that or not. If you want to think about it, if you want to not worry about it, don't worry. You don't need to worry about it. But what I'm going to do now is, instead of making a plot of velocity over substrate concentration, I'm going to make a plot of 1 over velocity over 1 against 1 over the substrate concentration. That's why it's called a double reciprocal plot. So if I plot 1 over the velocity as a function of 1 over the substrate concentration, instead of the data coming out in a hyperbola, they come out in a straight line. And I get more accurate results. I get a more accurate prediction of the Vmax and the Km. Okay, and your homework exercise, the next homework exercise, it's due a week from today. If you have a chance to take a look at it, maybe take a chance to look at it, but it's basically asking you to deal with something like this. So I can have a computer fit a line to those data. Have any of you, have you done that before? Have you put data into a computer and had the computer fit a line to it? Mm-hmm. You're with me, Jonathan? Okay, so I could put these data in a computer and it's going to tell me something like y equals 0.5x plus 10. I just made that up. So what is it? That's my slope. That's my y-intercept. So if I can have the computer spit out for me a slope and a y-intercept, so that means my 10 equals 1 over Vmax. So my Vmax would equal 1 over 10. My Vmax in that case is 0.1. And my slope is equal to Km over Vmax. And I've got my Vmax is 0.1. And I could do the math there, cross multiply that. 0.1 times would be 0.00, no, 0.05 would be my Km. So the Michaelis-Menten equation relates the velocity and the substrate concentration. Okay, from that, I can determine, for an enzyme, I can determine its Vmax and its Km. That tells me something about the enzyme. That tells me how fast it can work. That tells me how good it binds to its substrate. Okay, so I can get the Vmax and Km. Great. That equation, genius, whatever, the people have figured that out. Somebody else figured out, well, we can get the data better by just flipping it over and turning it into a line. So the Lineweaver-Burke turns it into a line. And I'm going to stop there. I've just got a little bit left. So the last thing we'll look at is how this is affected when we add an inhibitor. And again, this stuff is probably very esoteric. It's like, what is going on here, whatever. Yeah, maybe as we finish things off again, if you go into medicine, pharmacy, anything like that, you're going to find a fair amount of medications, a fair amount of things that you're giving people are enzyme inhibitors, or are things that act on enzymes. So we'll finish off talking about that. That'll be the end of Unit 2. So I'll finish up, almost done. If you have a chance before Thursday to think about, look things over, it's not going to take me anywhere near the entire class to finish this off. I can probably finish this off in 10 or 15 minutes, so we can use other time to review. So what are we talking about here? What's going to be coming up? Amino acid structure. So the amino acid structure, again, you don't need to memorize all the different structures. You need to know the basic structure. So again, everybody here by next Thursday should be able to do there are different ways you can draw it, but everybody should know that. So if I give you the R, you should be able to draw for me the whole amino acid. Understand what's going on with the pKs. Understand what's going on with the pK values. Below the pK, we're protonated. Above the pK, we're deprotonated. Know how that's going to do that. So we got the pKs, we got calculated PI. So review that, think about that. I'm going to give you an amino acid where it's got the alpha amino with a pK, it's got the carboxyl with a pK, and the R group is going to have an amino group or a carboxyl group or something with a third pK. So I'm going to give you an amino acid with 3 pK values and ask you to calculate the PI. So we've got Thursday to review. You've got Tuesday if you come up with, you got Tuesday too if you come up with a question. And then this chapter is really descriptive. So there's not a lot of calculations or, so protein structure, we talked a little bit about know the basic difference between an alpha helix and a beta sheet.
And you also said the 2 questions from the last quiz going to be on there? From the last test? We had to do the pKa minus log, pKa
Oh,
negative
right,
log,
correct. So I'm going to want, so from the previous exam, if I give you, so 2 things. So one is I'm going to give you a question where I give you the concentration of a strong acid or a strong base, and you tell me the pH. So I don't know yet, it's either going to be HCl or it's going to be sodium hydroxide or something. I'm going to give you a concentration. You're going to have to calculate the pH. Do not break out the Henderson-Hasselbalch pK thing. It's if I tell you that HCl, the concentration is 0.0007 molar, that's your proton concentration. And how do you get the pH of that? Negative log. Negative log. Don't do pH, pK stuff. So when it's a strong acid, you just get the... If I were to give you the same number for sodium hydroxide, then that's your OH concentration. You take the negative log of that, that's your POH. You got to do one more thing. We just subtract that number from 14. So I'm going to make it do that again. And then the other thing we're going to do is, I will give you something using the Henderson-Hasselbalch equation where I'll give you give you a pK and pH. So Henderson-Hasselbalch pH equals pKa plus log base over acid, where I'm going to ask you to calculate the ratio of the acid form base form. I'm going to write myself a note, and I will I'll see if I can enter so that it won't be for points, but I'll just see if I can enter something in Canvas tonight or tomorrow morning. I'll make a couple practice questions on these 2 things. And we can talk about that on Thursday. All right, so all right, so I'll come up with something for you there. And we'll finish this chapter off and do some review on Thursday. Yeah. I got yours. I don't know if you saw my reply yet, but it was all.
Oh, the
no.
homework.
Did you? When did you send me the homework?
Today.
Okay. Maybe I haven't.
I don't think you've seen it.
Okay, never mind. Yeah,
But
okay.
it's in the comment of it. of
Okay.
the assignment, yeah.
Got it. All right. this was for the, all right, see ya. Right, okay, I will, that's all correct. Okay, so, and you've got yours there. All right, see ya.
Professor, on my homework, I had left it at my job, so can I email it
Send it to
you?
me as soon as you're able.
Thank you.
2 millimolar, 6 millimolar. So Jonathan, this is all good. So I'm just gonna hand it back to you. So I made a note